Welcome to this presentation on controller design approach. In this presentation, we will suppose that our plant is a continuous time system, and for the reasons explained earlier, we would want our controller to be implemented as a discrete time system. How are they connected? One is a continuous time system, the other is a discrete time system. How are they connected? How do they understand each other? These are the points that will be explained in this presentation. Suppose that a plant is described in continuous time as follows. It's in the standard state space form. Here is a schematic of a closed loop system or a feedback control system where we have the plant that needs to be controlled with the help of this controller. Here is the reference signal or the set point. Here is the actual value that is achieved. The difference between R and Y is E, the error signal. Depending on the value of the error signal, the controller output is determined. This is the input to the plant. This is also known as the manipulated variable. Here is a disturbance variable V that affects the plant output. So this Y is the disturbance affected variable that comes from the plant. So the plant is a continuous time unit and the controller is a discrete time unit. The controller looks at values only at time instants. That's what is meant by a discrete time unit. The controller cannot handle continuous time signals. So how do we connect the plant output to the controller? So we will see in the next slide that it is through A to D converters. A to D converter samples analog signal and produces binary equivalent. This is a batch process, that is production of binary equivalent. Conversion of a continuous value into a quantized value is a batch process. It requires non-zero time. So the resulting signal is discrete in time. We will denote it symbolically as follows. So in this graph, the input is the analog signal. It is denoted by this continuous graph. The A to D converter picks this signal at this value, quantizes it. That means the A to D converter samples the signal at this point. It's here, it's here, it's here, and so on. But unfortunately, it can only represent in specific levels. For example, it can store it as this value or this value or this value and so on. So this value will be approximated as this value will be approximated as this, the nearest quantum available. To do this conversion, it requires time. For example, it picks up and then it has to convert it to the nearest value here and then stores it. That takes time. By the time next signal comes, it picks the next value and so on. Okay. So what we get is a quantized sampled data. This is what is sent as the digital signal by the A to D converter. Of course, in naturally discrete time plants, there is no need for A to D conversion. So there are two issues. One is what are the approximations that happen here and what is the time gap between two samples. So the first issue is the quantization error. Finiteness of bits results in quantization errors. For example, if the number 1 by 3 has to be denoted as 0.3, then there is a very large error of 0.03. If instead you write it as 0.33, then you have smaller error, but you still have error. We can increase the number of bits to reduce errors. Falling hardware prices help achieve this. Sampling rate, as I mentioned earlier, if you sample very slowly, that is the time gap between two samples is very large, then we could lose a lot of information, whereas if we sample at a very high rate, there could be a computational load. We will discuss this topic in detail later in the sampling rate. We will assume in this course that we have sufficient number of bits, and hence we do not have to worry about this quantization error. Alright, now let us send the controller output to the plant. Remember, output of the controller is a digital signal, it is discrete in time, and suppose that has to be sent to a plant that is continuous time. How does the plant work with the digital signal? In particular, what value should it use in between sampling instants? For example, this value has to be understood by a valve. The controller sends values only at sampling instants, so the valve needs to know at what value its position should be in between two sampling instants. It is handled through D to A converters or digital to analog converters. Here is the sample signal, this is the signal that is sent by the controller. What value to keep between sampling instants? An easy way is to hold the value constant through zero order hold. The phrase zero order hold is used because a constant value is a 0-degree polynomial. Notice that I put a dot here, that means the value at this instant is used throughout this interval except at the next instant when the value obtained at that instant is used. Here is the zero order hold scheme. There are many other hold schemes as well in the literature, but zero order hold is the most popular one. We shall consider only the zero order hold in this course. So we will assume the use of zero order hold in this course. In particular, we will assume all inputs to be of zero order hold. This is okay when the input is produced by a digital device because it uses a zero order hold. It is also okay when the input signal varies slowly. This approximation will help arrive at simple models. We will see this soon. Summary, we will now see the way continuous and discrete systems are connected. The signal E, which is analog or continuous, which comes from the plant, for example, it is sent through a digital signal using an A to D converter. The controller produces digital output. It is converted to a continuous signal using D to A converter. Although it is not shown here, it is to be used, and the output of the D to A converter is sent to the plant. Here is a sample graphical program where we have shown the zero order hold explicitly. The A to D converter, however, need not be shown explicitly in this representation. Zero order hold is shown explicitly, as I mentioned earlier. The next question we have to understand is, alright, we have connected, but how does the controller understand the plant? Because the plant is described in continuous time and controller is a discrete time unit. The controller has to understand the plant to take corrective steps. How does the controller view the plant? It receives and sends out sample signals thus views the plant also as a sampled system. The digital controller does not understand continuous time systems, derivatives, etc. There are two approaches to design the controller. The plant is first discretized. Using this, the controller is designed in discrete time, and of course the controller can also be implemented directly because it is a discrete time unit. But before implementing it on the real plant, which we have assumed to be continuous time, we first have to validate it through simulation. We will first validate it through simulation and then only put it on the real plant. The second approach is the continuous time plant is not at all discretized, it is kept as a continuous time plant. We will design a continuous time controller directly for this continuous time plant. So, a controller will naturally be in continuous time. We then discretize the controller for implementation. In this course, we will use the first approach. What is that? We will discretize the plant and we will design the controller in discrete time directly. Okay, we will discretize the plant. What are the reasons that we have chosen this approach? One is efficiency. Controllers designed in continuous time have to be sampled at a much higher rate. That is the second approach we talked about, could require a very high sampling rate, 10 times or more. So, the special features of discrete time systems can be used effectively. One could argue that it is possible to handle very high sampling rates. After all, the computer prices are falling and so on. But remember, compared to a low end device, we would need lot more powerful systems to handle high sampling rate, and this will become especially crucial when we want to produce very low cost devices, which could be an important factor in a large country like India. It could also be important in situations where we might need really rugged devices, and rugged devices could be used only in very limited number of cases. So, the argument of more powerful devices being available at low price may not be applicable. So, efficiency is one reason. The other reason is a much larger class of controllers are available in discrete time domain, and there may not be an equivalent continuous time equivalent. And there are references available in the textbook for these points. With this, we come to the end of this presentation. Thanks for joining. Goodbye.